So we're working still on solving polynomial equations, but this time all of our solutions, all of our zeros are not going to be real numbers. We're going to get some complex zeros and thus finish up with the fundamental theorem of algebra. So just here's a list of some theorems to know. Some of them we've already talked about. The first one, the factor theorem, we talked about this last class. If C is a zero of the polynomial, then x minus c is a factor, and vice versa. So, for example, if you know that 5 is a 0, then x minus 5 is a factor, and if x plus 8 is a factor, then you automatically know that negative 8 is a 0. Okay? Multiplicity, another, not necessarily theorem, but definition we need to know, the number of times a 0 or a factor repeats, that's multiplicity. So if you have the polynomial x minus 4 to the third power, it has a 0 at the number 4 of multiplicity 3, which means that this would cross, since odd multiplicity means it crosses the x-axis. That other polynomial, x plus 2, has a 0 at negative 2 of multiplicity 2, and since that's an even multiplicity, it's going to bounce off the x-axis at that location. Our next theorem to know is the complex conjugate zeros. Now, this is more of a definition as well, but it kind of lends itself to a theorem. It says if x equals a plus bi, so a complex number, is a zero of a polynomial, then x equals to a minus bi, which is called the conjugate, is also a zero. Okay, so imaginary solutions, imaginary zeros come in pairs. If you know a plus bi is a 0, then the conjugate a minus bi is automatically also a 0. So if we have 3 minus 5i as a 0, that means we automatically know that 3 plus 5i is also a 0. And if 1 plus I is a 0, that means automatically we know 1 minus I is also a 0. Our two theorems for today that we're going to be focusing on a lot is the fundamental theorem of algebra. Okay, fundamental theorem of algebra, I would put a little star next to this one. A polynomial function degree n has n total zeros, which we knew this already. We were already seeing this pattern. However, today we're going to have some of those zeros being repeated, some of them being real, and some of them being imaginary or complex numbers or non-real numbers. So the polynomial that you see here, x to the third power plus 5x to the fourth power minus 3x to the second power plus 5x minus 2, since the degree of that polynomial is 4, the largest exponent, that means that this is going to have 4 zeros. Some of them might be repeated zeros, some of them might be real numbers, and some of them may be imaginary numbers. The polynomial 2x to the fifth minus 7x cubed minus x plus 10, since the degree of that polynomial is 5, it's going to have 5 zeros. That makes sense. The last theorem we're going to be working with today is called the factors of a polynomial with real coefficients theorem. So it's a theorem and kind of a idea here as well. It says every polynomial function with real coefficients can be written as the product of linear factors as well as what are called irreducible quadratic factors, each with real coefficients. Now, an irreducible quadratic factor is a quadratic with no real solutions, which means it's probably going to have two complex zeros or two imaginary zeros. The polynomial here that you see, x cubed minus 2x or minus x squared minus x minus 10 can be factored and written as you see here, where we have a linear factor, x plus 2, and a irreducible quadratic factor, x squared minus 3x plus 5. If we tried to factor and solve, or even use the quadratic formula, we'd end up having imaginary solutions. Now remember, every imaginary zero has a pair, so we should have two imaginary solutions when we have an irreducible quadratic factor. They always come in pairs. Okay, let's use some of these theorems here to answer these questions in example 1. It says, suppose you have the polynomial with the zeros, x equal to 2, negative 2, sorry, and x equal to 3 plus I. Well, automatically, using that complex conjugate theorem, we also know that we also have 3 minus I as a solution. So how many zeros do I actually have in this function? I have 1, 2, 3 zeros, and the fundamental theorem of algebra tells me that the minimum degree that this is going to have is 3. So to write a polynomial in factored form, not multiplying anything out just yet, with these given zeros would be x in a positive 2, and then x minus 3 plus I, and x minus 3 minus I. Don't worry about distributing that negative just now, we don't really need to. But that's factored form with those zeros showing as linear factors. But what we're going to also do is be able to write this as the product of linear, so we already got our linear up there, and our irreducible quadratic factors, which really means that we're going to need to multiply these two factors here with the imaginary numbers, this one and this one, together so that we have an irreducible quadratic factor. Because that looks complicated up there, and we can multiply them together and have a quadratic and write it as a product of that linear x plus 2 and then the irreducible quadratic factors. Now you totally could FOIL this thing, but it's hefty if you actually FOIL it. So we're going to write down a shortcut to FOILing that I highly recommend taking, especially when you're multiplying polynomials with imaginary numbers. The shortcut is that when you're multiplying, it's always x squared, and then subtract the sum with an x next to it and add the product. Okay, I will show you how to use this shortcut here, but it's a shortcut for multiplying polynomials together. Okay, now this also, again, I know I'm sorry I can't show you what I'm doing in my calculator, but there is an imaginary button, so look for the I on your calculator. You're going to be using that I button. It's second and then some button so that the I is blue. But you can actually do the sum, so 3 plus I plus 3 minus I. You can type that all in your calculator. It's going to give you 6. And you can also find the product, 3 plus I times 3 minus I. That would give you 10 if you throw that in your calculator. So I automatically know that this second two polynomials, linear factors here, would multiply using the shortcut to x squared minus 6x plus 10, where that is a irreducible quadratic factor and x plus 2 is a linear factor. Again, that's a linear factor, and that's an irreducible quadratic factor. Again, I just took a shortcut here when I'm multiplying those polynomials together. I'm going to use this subtraction of the sum and then add the product. In the link or in the description of this video, I'll put a link to another teacher who does have a way to show you a calculator on his screen. So if you're like, what in the world, Miss Quigley? I'll show you that in a second. Or you can go down there and look at it. Now, the last thing we're going to do is we're going to write this polynomial that we've boxed in part C in standard form. Remember, standard form means we don't have any parentheses and we're writing it from the largest exponent to the smallest. So we're still using the same zeros, which means all we're going to do is multiply x plus 2 times x squared minus 6x plus 10. There's no shortcut when we're multiplying not a binomial times a binomial. This is a binomial times a trinomial, so you're just going to have to do double distribution. So we'll do x times x squared, that's x cubed. X times negative 6x, that's negative 6x squared. X times 10 is 10x. Then I'm going to do 2 times x squared, but I'm going to put that sum or that product underneath so I can line up my like terms. 2 times negative 6x, that's negative 12x. And 2 times 10, that's 20. I'm going to add these things together, combining my like terms. It's a nice little addition problem here. And voila! I have written my polynomial in standard form, which means it's in decreasing exponent order, 3, 2, 1, 0. Example 2 will help us prove that complex conjugate idea. So we have this polynomial given, and we're told that one of the zeros is x equal to 2 plus I. Okay, so let's check with synthetic division to make sure that it really is a 0. So synthetic division, we put the number we think the 0 is on the outside, yes, the entire complex number, and then all of the coefficients for that, in this case, quadratic, for the polynomial. Bring down, multiply, add, multiply, add, multiply, add. Again, you can use that calculator to multiply and add these complex numbers if you need to. And you should see that when you multiply 2 plus I times negative 2 plus I, you end up with negative 5, which is nice because, again, we need our remainder to be 0 to prove that something is a factor. So there we have proven that it really is a 0 of the function, check, because we got a remainder of 0. Therefore, it is a 0, and that it becomes a factor. And we need to find the other solution. Well, based on my quotient here, we have 1x and a constant of negative 2 plus I. Well, I want to solve that for 0, because just like the zero product property says, I can take each factor and set it equal to 0, which means I'm going to add 2 to both sides and subtract I to both sides. Our other 0 is at 2 minus I. That's our other solution here, which is exactly what we know based on that complex conjugate, that if I have 2 plus I have to have 2 minus I as one of my other zeros. That's this conjugate theorem right here. So we know that the expression x squared minus 4x plus 5 could be factored to the following. X minus 2 plus I, that's the 0 they gave me, and x minus 2 plus I, which is the 0 we found using either the theorem or this synthetic division. In example 3, we're going to write a polynomial function of minimum degree in standard form, so again, no more parentheses, whose given zeros and their multiplicities include those listed below. Okay, so let's look at example A. Here we have the zeros of negative 5 and 4i. Now, immediately you should also be like, okay, well that's positive 4i. I also have negative 4i as a 0. Which means that this polynomial, since it has 3 zeros, should have a degree of 3. That's just a good check for ourselves to make sure we got where we wanted when we finish this problem. Okay, so what we're going to do is we're going to multiply the factors created from this particular set of zeros. The factors would be x plus 5, x minus 4i, and x plus 4i. Okay, let's use that shortcut again. So I'm going to use a shortcut to multiply the back two together. I'm going to multiply these right here. Our shortcut says that we need the sum and the product. Now the sum of minus 4i and plus 4i, well, that's 0. And the product of minus 4i times 4i, you can check me in your calculator if you don't believe me, is 16. Which means that those back two binomials will multiply together to x squared minus 0i, so I don't need to write it, minus 0x, sorry, plus 16. And now I can FOIL like normal. X times x squared is x cubed, x times 16 is 16x, 5 times x squared is positive x squared, And 5 times 16, that's positive 80. So if I add all my like terms together, my standard form polynomial is x cubed plus 5x squared plus 16x plus 80. All we've done is we foiled together all of those polynomials. I just took a shortcut using the sum and product idea for multiplying binomials. And if you don't get that shortcut, you can FOIL all that out. But a question like B here is going to really ask us to be very good at using that shortcut. Otherwise, you probably need like triple the amount of paper to do this problem. All right, so we're given the zeros. We're given the zeros of negative 2 with a multiplicity of 2 and x equal to 2 plus 3i. Your spidey senses should be going off because hopefully you're thinking, we also have 2 minus 3i. And since this is multiplicity 2, that means this x equals to negative 2 happens twice. So this is actually going to end up being a degree 4 polynomial. Sweet, so here's what it looks like before we start multiplying. We're going to have x plus 2 times x plus 2 times x minus 2 plus 3i and x minus 2 minus 3i. You could FOIL this out the regular way, but it's going to take you, like I said, like 3 times the amount of paper to do that. So let's utilize these shortcuts. For the first set, we can do the sum, and we can do the product. Therefore, those first two binomials will multiply or FOIL out to x squared minus the sum, so minus 4 times x, plus the product. My second two binomials here, these are the ones we especially want to use the shortcut for. We want to do the sum of 2 plus 3i and 2 minus 3i. And in your brain or in your calculator, you'd get that those are 4. And you're going to use the product of 2 plus 3i and 2 minus 3i. Again, I highly recommend utilizing your calculator for this imaginary numbers. You'd multiply those, you'd get 13. Which means that our second set of binomials multiply or FOIL out to x squared minus the sum plus the product. And thanks to that shortcut, at this point I have no more imaginary numbers left, and so I can just double distribute, in this case triple distribute, like normal. Now I'm going to do this very strategically so that I have all of my like terms lined up. First start with your x squared term. You're going to multiply x squared times x squared, that's x to the 4th. X squared times negative 4x, that's negative 4x cubed. And then you have 13x squared. Then you switch, you're going to distribute the second term in the first parentheses. 4x times x squared, that's 4x cubed. 4x times negative 4, negative 16x squared. And 4x times 13, that's positive 52x. Then I'm going to multiply this last constant here, 4, times everything in that second parentheses. 4 times x squared is 4x squared. 4 times negative 4x is negative 16x. And 4 times 13 is positive 52. If you do this like this like waterfall looking thing, notice that now all of my like terms are lined up. So I can just add straight down so that I get all of my like terms without having to do any sort of rearranging to get my final polynomial. And this polynomial here, x to the 4th power plus x squared plus 36x plus 52, would have 4 different zeros. 2 of them are a repeating negative 2, 0, and then the imaginary solutions 2 plus or minus 3i. All right, let's talk about the fundamental theorem of algebra again. So what is the fundamental theorem of algebra? And we've kind of been using this idea for a while, but basically the fundamental theorem of algebra is that the degree of the polynomials should equal the total number of zeros. We just now know that some of those zeros may be imaginary and some of them may be real. And that's why we need the fundamental theorem of algebra to tell us how many real versus imaginary solutions or zeros our graph or our function is going to have. So use the equations in the graphs below to identify the number of zeros according to the fundamental theorem of algebra and determine how many real and non-real zeros each function has according to the graph. So let's zoom in here for a second at A. Based on the fact that A has a degree of 4, we know that it should have 4 zeros. If you look at this graph, there are only 2 of the real zeros showing on the graph, here and there, because our zeros are our x-intercepts, which means if I know that there are 4 zeros of this function and I only see 2 real ones, therefore there are 2 imaginary solutions. Which makes sense because you can't have one imaginary solution. You're always going to have at least a pair of them, so 2, 4, 6, 8, or 10. So if we have 2 real ones showing and we know it's a degree 4 polynomial, we have to have 2 imaginary solutions. If we look at B, the degree of B is 3, which means it should have 3 total zeros, and there's only 1 real zero showing. Okay, again, the zeros is where the graph crosses the x-axis. Therefore, there are 2 unaccounted for zeros, so we have 2 imaginary solutions, or 2 non-real solutions, which is great. That's super good information for us to know, and that's thanks to the fundamental theorem of algebra. Now, question 3 says, how many real zeros are you guaranteed to have if you have an odd degree polynomial? Okay, we just kind of talked about this, but write this down for yourself again. Remember, the imaginary zeros are complex zeros here, a plus or minus bi. They have to come in pairs. So, because if it's a plus b to the I, you also have a minus b to the I as a zero. So let's just see how many real zeros we have if we'd have some odd degree polynomial. For example, let's say you have a degree 7. We have a degree 7 polynomial. All of my imaginary numbers come in pairs, which means I could have up to 6 imaginary or complex zeros, because they have to be in pairs. That means if I have an odd degree function, any odd degree function, I'm guaranteed to have at least 1 real zero, because the imaginary ones come in pairs. So we'd have to have an even number to have totally imaginary solutions or zeros. If you have an odd number, there's at least 1 real one, which is pretty good to know. Utilizing, again, that fundamental theorem of algebra, we're going to look at example 4. It asks, is it possible to find a polynomial f of x that has a degree 4 with the given zeros? Okay, if you look at A, you have the zeros of -3, x plus 2i, and x minus I. But hopefully you should also realize that that means that we also have x minus 2i and 1 plus I. So in total, I actually have 5 zeros because of those complex conjugates, which means that this would be a degree 5 polynomial. So no, we can't have a degree 4 polynomial. This has 5 zeros. If you look at B, it shows us that we have the zeros 1 minus 3i and 4 plus I, but you have to know that that's also 1 plus 3i and 4 minus I. That's a total of 4 zeros Therefore, this has to be a degree 4 function. So yeah, this one should be a degree 4 function. All right, if we look at example 5 here, this is actually a really good example to work with, example 5, A and B. It says, using the given 0, find all of the zeros of the polynomial function. These are like if last class we found these numbers off our potential rational zeros list. So we know that these are zeros, okay? We're going to synthetically divide them into this polynomial. So I set up synthetic division. I have 5, 3, 3, 3, negative 2. Interesting. Bring down, multiply, add, multiply, add, multiply, add, multiply, add. Synthetically divide again, but this time by 2/5. You can multiply and add by a fraction. Utilize a calculator if you need more help. Multiply, add, multiply, add, multiply, add. So it tells me those two zeros, and then I'm left with this irreducible quadratic factor. This irreducible quadratic factor is 5x to the second power plus 0x plus 5. Now, that's nice, but I actually need to find out what the zeros of this irreducible quadratic factor is. If you have a binomial, you can solve by square rooting this. Solve for x like normal. So we're going to subtract 5 to both sides. We're going to divide by 5 on both sides. We're going to square root both sides. And hopefully you remember that the square root of negative 1, that's I. Which means if we were to find all of the zeros of this function, all of the zeros are negative 1 and 2/5, which were given to me, but then also plus or minus I. So not only am I getting down to that irreducible quadratic factor, I actually have to solve that irreducible quadratic factor for its solution or its zeros to include that those two, it always come in pairs if you have an imaginary solution, as part of my zeros for the polynomial function. Let's do the same thing for B. B says that we have a solution at 2 plus I, and hopefully you're thinking, well, that also means we have 2 minus I because of the complex conjugate. So we can synthetically divide by both of these zeros. 1, negative 4, 36, and negative 45. Bring down, multiply. Again, at this point we are using an imaginary number, but you can do this part in your calculator if you need help with it. Multiply, add, multiply, add, multiply, add. Phew. It's ugly, but we got a remainder of 0. That means we know it's a factor, which is a given. Repeat. Bring down, multiply, add, multiply, add, and on until you get another remainder of 0. Yay! Remainder constant x squared. Now this time my quotient here is not actually an irreducible quadratic factor, because if you notice, we could solve this quadratic and we'd actually get real solutions. This is x squared minus 9. You might notice that it's the difference of 2 squares, but if not, you would just solve for x. And the square root of 9, well, that's the real number 3. So my list of zeros for this, I have 2 imaginary numbers that were given. And I have my real solutions, giving me a total of 4 solutions for this polynomial, which matches the degree. Example 6 wants me to factor the polynomial, not necessarily solve it, so we're going to write it with a linear factor and then an irreducible quadratic factor. But this is actually a very interesting example because I'm going to zoom in here. The scale is 1 tick. Okay, we all read that part. The degree of this polynomial is 4. Degree is 4. How many real solutions are shown on the graph? There's one real solution shown. One real zero shown. And since imaginary solutions come in pairs, we know that there has to be 2 imaginary solutions. Can't be 3 imaginary zeros. So therefore, there is one more real zero somewhere. And a real zero is going to show up on this graph. And hopefully you're noticing, wait, but Miss Quigley, at 2, it bounces off. Yeah, that's true. So therefore, x equal to 2 has a multiplicity of 2. It bounces off at 2. So I have my 2 real solutions. I know it's 2 and then 2. That gives me exactly what I need to start dividing by to synthetically divide this polynomial and then factor it of -2 and then -2 again. I'm sorry, not -2, 2 and then 2 again. So we synthetically divide like we've been doing. And then we synthetically divide again with that repeated value. So that I have, in the end, my quotient. Now this quotient this time is actually going to become an irreducible quadratic factor again. And if we were solving this, which we're not, we're just factoring it, we'd have to use the quadratic formula to solve that irreducible quadratic factor. But all we're doing is factoring g of x here. So g of x is equal to what we see on the graph of x minus 2 with multiplicity 2 multiplied by that irreducible quadratic factor we got as our quotient, 3x squared plus x plus 2. Remember, this is linear. I can solve it. This is an irreducible quadratic factor. For the examples here in the last page, we're just going to look at work because we've done these steps over and over again. So I think just seeing an example all the way through would be helpful. Obviously, you can pause the video and write down all of these notes. In examples 7 and 8, you're going to be given a function. We can always quick check the degree. We should find 4 zeros for this. But we're going to start off by finding the possible rational zeros. Remember from last class that that was P and Q. And we take all of the p's and put them over all of the q's to give a list of possible rational zeros. We're not talking about irrational numbers or imaginary numbers, just our rational zeros, but it's a good place to start. We'd find in our calculators which one of them has a remainder of 0 when we evaluate the function at that particular point using our table. And that way we know what we're going to synthetically divide by. So we would synthetically divide by -4, we'd synthetically divide by 1/3, and end up with a quotient. Okay, that quotient is 3x squared minus 12x plus 15. Now, we know that we need to find 4 zeros, and we only found 2. Most likely, those are imaginary, if not irrational. In this case, they'll be imaginary. So if we wanted to solve this quadratic, the most straightforward way to do, since this is a trinomial, instead of just, quick solving for x, we're going to have to use the quadratic formula. That's x equals -b, opposite of b, plus or minus the square root of b squared minus 4 times a times c, all over 2 times a. You're just going to start simplifying like normal. So we calculate what's underneath the square root. We would take the square root if possible, remembering that if it's negative, you have an I, because the square root of -1 is I. And then calculating, again, my 2 imaginary solutions. my imaginary zeros. So therefore we know the zeros of this function are -4, 1/3, and what we got from our irreducible quadratic factor when we solved it, probably using the quadratic formula. Okay, we got the zeros, and the easy part here now is writing the function as a product of linear, so what we get from our rational zeros, and irreducible quadratic factors, just truly my quotient here after I synthetically divide. And that's what we're going to do for example 8, for both parts of example 8. I'm not going to really talk you through these because you can kind of pause it and see what I did. I followed the same steps every time of finding, finding the potential rational zeros, dividing by them, ending up with our irreducible quadratic factor, my quotient, and then using the quadratic formula when needed to be able to solve for my imaginary solutions. If you have a binomial of your irreducible quadratic factor, you don't have to use the quadratic formula. You still can, but you can just solve for x like normal. If you have any questions about these examples after you look through them and write them down, make sure you bring those questions to class.